All right, here's a little help getting through this homework assignment, at least problems 1 through 7. Long division on the first part. We did this in class for most of you guys today. So here's a look at long division. Again, 3x into that first term, 3x cubed goes in x squared times, and then you multiply that back times the 3x plus 2 to get the result that you see down below there. Change the sign and add them. That's important. Change the sign of both and then add them down. It's the same effect as subtracting. And then once you get the result, 3x squared, then you bring down the next term, 8x. Figure out how many times 3x goes into that 3x squared. Goes in x times. Multiply through the 3x plus 2. Get that result. And then we change the signs and add down. Bring down the 7. 3x goes into 6x 2 times. Multiply through. Change the signs, add down. We got a remainder of 3 over x plus 2 I wrote the first time, but later on I'll go back and add that 3 in there. Should be 3 over 3x plus 2. There it is. Next is a nice synthetic division problem. Just make sure you put in the coefficients. None of them are missing. Always keep track of that. We got an x cubed, an x squared, an x, and a constant. So they're all there. 2 comes down. Multiply 3 times 2. Get the next term. Add down. Multiply, add down. Multiply, add down. When you get a remainder of 0, you find out that 3, that root I'm dividing in, which indicates a factor of x minus 3. Remember, if you've got a root of 3, you have x minus 3 as a factor. So if you have a root of whatever number a, you have x minus a as a factor of the original polynomial. So yeah, this one works. The most important thing, though, is when you find out x minus 3 is a factor, is that means x minus 3 times that 2x squared plus 3x plus 4 piece you got, your quotient. Multiply those two together, you get the original. And keep that in mind, that's really important. On to the next page, P's and Q's. We got to find the possible rational zeros. So I just need a list of all the Q over P possibilities. And here they are. You just do a ratio of all those. It's a simple request. But now it says, hey, prove 1 is the upper bound for the zeros in that function. That's the biggest one. And what you do is there's a numerical reason for why it's the upper bound, but you can also look graphically and see it's the largest of those. We'll talk more about the numerical analytical part later on, but just bring down your 3, multiply by 3, and then you get add them, the process of synthetic division, which I know you guys have down. What we get is a remainder of 0. We find out that because 1 went in, x minus 1. So make sure, you understand the concept that factor that you got, that x minus 1, times the quotient gives you the original. Huge deal. All right, so now, there's a little rhyme. I wrote something, I forgot about that. Now number 5, you've got the whole polynomial there. It says find all the real zeros. Real zeros, just any real number. That just means find all of them, basically, that are not imaginary. So the ones that you can. So we start with this PQ stuff. And Q over P gives you all your options. I think you could probably get the idea of what they are without having to write them. This is just a quick list, and my handwriting gets just terrible. But it's all those things over 5 plus all of the Q factors, because if you put them over 1, you get the same thing. That's a lot to choose from. So when you're trying to limit that, you want to look at some kind of reference, like a graph, and say, hey, looks like maybe it's this one. So you can kind of save time that way. So a couple of them that I found, and I think I did it on the next page. Let's see if I can find this. Is that over here? Yeah, I think that's the one. 5, negative 2. Sorry, I have to look over my screen. Let me go back another page. Is that right? 5, negative 12. Yep, there they are. So if I go to this page, that's looking at negative 2, looked like one of them. So I ran it through. And after I did negative 2, I get this result with a remainder of 0. That was good. So that's good. I know x plus 2 is a factor. And then I did 3, looked like one of them. So I put 3 in there, and I did my long division. Got this result. 0 remainder. Awesome. So x minus 3 is a factor. And then it looks like, if you look at that graph, 7/5 is 1.4, probably works in there. I mean, you're just testing values, looking at what the graph suggests. If you divide in that synthetically, as you see below, we get this result. And that means you're done. Now, remember, all those, I found out that each of those was a factor above, but the key is, when you're done, the actual polynomial is not just x plus 2. times x plus 3, or minus 3, times x minus 5, or 7/5, if you just graph those three multiplied together, your function, and then you graph the original, if you were to do the product of those three factors and then compare it to that original function that I have underlined up there, they aren't the same. What you're missing is the times 5 that this suggests down here. So if you're left with that constant 5, remember this implies that 5 times x minus 7/5 gives you this function here that you were dividing into in the first place. So that times 5 actually becomes really important. That's our constant. And this is the one example where that shows up. So be careful as you're going through synthetic division. We don't want to lose that times 5 at the end. So anyhow, back to 6. The last one was just to find all the real zeros, by the way. So you just needed to find that all those factors were, 2, -3, and so on. So here's number 6. The first thing you want to do in this, if all of your terms have an x in them or a power of x that you can factor out, do that first, because x equals 0 is going to be one of your roots. Now the next piece is, now we're going to go in and play around with the internal part of it that's left. We can do p's and q's and get some possible roots. Okay, and then we can just start working with a graph and see what works. Well, you look at your graph, try -1. It's a good option. So if you graph it, you'll see that that's a possibility. And you'll run through synthetically, see if you get a remainder or not. Looks like we're good. That means x plus 1 is in fact a factor. But you want to remember that it's not just that x plus 1 is a factor, it's x plus 1 times this chunk here is equivalent to the original. So now we need to deal with factoring that 2x squared plus x minus 15 that's left. We need to take that apart, see if that busts up, find its zeros. So remember, finding the zeros is finding out where this thing is equal to 0. Right now we know that -1 is one of our options. If we could just factor that quadratic there, we could find maybe 2 more roots. Okay, so we're going to go for it. If you look at the graph, you'll see -3 looks like one of the possibilities. Kind of looks like -1 and -3 if you graph it. So I'm going to try that, run it through the last part of that quadratic, see if it goes through evenly. Yes, it does. What that means, remember, is that x plus 3 and that 2x minus 5 multiply together to make that quadratic. And sorry, I got a little gooey in there. I'm going to try and clean that up a little bit. Let's see if I can clean that. There you go. That's x plus 3 times that 2x minus 5 that we get as the quotient. Remember, equal the quadratic that we were dividing into in the first place. Okay, so that's our whole polynomial. Look what we got. X plus 1 times x plus 3 times 2x minus 5 makes that original function minus, remember what we did, remember we factored out an x early on, so that x also goes out front. That's your original function if you multiply those out. Okay, so there you go, and our roots are -1, -3, 5/2, and of course 0. Don't forget that one. And on to number 7. Okay, this is imaginary. The imaginary part is really important. If 4i is a 0 of a function, we'd say x minus 4i is a factor. Okay, in synthetic division and all that long division works great with imaginary numbers. It's the same kind of thing. So what you do for synthetic is you put 4i in the box, bring down the 1, and you proceed just as you would. Multiply by 4i. The thing you want to notice is that when I do 4i times 4i here, you see right there, that makes 6, and you look up here, it makes -16. 4 times 4 is 16, and the i's squared makes -1. And then you add down, same thing, you do 4i times -3 is -12i, add down you get -12i, and then 4i times -12i, you get -48 times I squared. And remember, just the biggest reminder is I squared is -1. And if you remember that, that's where you get all these values with I. The end result, I have written down below there. That's okay. It happens to be kind of an imaginary expression. Now, there's a bonus to having a 0 that's imaginary. It always comes in pairs. So right now what I've got is x minus 4i times my quotient there is equal to the original. My bonus is that x plus 4i is also a factor of the original function. So whenever you get 1 0, that's imaginary, you always have a second, which is the opposite sign of the original one. So here we are. We're going to try negative 4i as well. We're going to do long division on my leftover quotient there. Same process. Follow through. Do your multiplication. Add down just like you would in any other case. And then the final step, it might look kind of weird, but negative 4i times negative 3 makes positive 12i. And hey, guess what? That's the opposite of what I have there. What I just found out is x plus 4i times x squared minus 3, that quotient, is equal to, what I had left over there that I had divided into originally. That's pretty exciting. So what we proved is two things. X plus 4i and x minus 4i are both factors, and we used it to write a full factored form of my original function. Let me write that again for you. We found that the original can be written as x plus or minus 4i, and then x squared times x squared minus 3. And we're supposed to find all the zeros? Well, that's easy. Negative 4i is one of them, positive 4i. And then we just need to solve that x squared minus 3 piece, which is, you guys know that, plus or minus radical 3. There's all the remaining zeros. All right, that's all for this one. I'll give you the rest of it in another video.